Let me help you ace your Precalculus Exam 2 by solving problems from Unit 5 on trigonometric functions of real numbers. Number 1. Consider the point P whose rectangular coordinates x and y are given by these two numbers, -3/5 and -4/5. Part A says to show that this point is on the unit circle. We'll have to use the equation of the unit circle to do that. Part B, suppose that P of xy is a terminal point determined by the real number t. I'm not talking about angles here. I'm thinking of t as being a pure real number. It is going to be related to an angle, but not yet. The goal is to find the values of the 6 trigonometric functions of t. All right, part A, to show that this point is on the unit circle, I need the equation of the unit circle. The equation of the unit circle is x squared plus y squared equals 1 squared, which is 1. Where does this come from? It's the Pythagorean theorem, or if you prefer, the distance formula, which is related to the Pythagorean theorem. To show this point with these rectangular coordinates is on the unit circle. That's a circle of radius 1, by the way, centered at the origin. We need to show that the coordinates x and y satisfy this equation. That's just a matter of substitution. Replace x with -3/5, replace y with -4/5, and simplify. Do we get 1? -3/5 squared is positive 9/25, and -4/5 squared is positive 16/25. These fractions have a common denominator of 25. We can add them by adding the numerators. 9 plus 16 over 25 is 25 over 25, which is 1. That's an algebraic confirmation that the point with these rectangular coordinates is on the unit circle in the xy plane. Again, the unit circle is a circle of radius 1 centered at the origin. So it looks about like this. This particular point with coordinates -3/5, -4/5, which would be -0.6, -0.8. Try to eyeball it. -0.6 is right around there on the x-axis, and -0.8 is right around here on the y-axis. Figure out where on the unit circle we get to from those points. It's right about there. There is our point P with rectangular coordinates -3/5, -4/5. All right. Part B, find again the values of the 6 trigonometric functions of t: cosine, sine, tangent, also secant, cosecant, and cotangent. How do you do that? We're going to, again, focus on the unit circle. I don't have to think about angles if I don't want to, though I can. I will hint at how to think about angles. What we just need are the coordinates of this point. We can define the 6 trigonometric functions in terms of those coordinates. In terms of the terminal point determined by the real number t, you start at the rightmost point of the unit circle, so to speak, the point whose coordinates are 1, 0, and you travel counterclockwise around the unit circle a distance, an arc length of t. To get to this point, you have to go about this far here, around there. How far is that? Think about this with me intuitively, and also based on knowledge about the circumference of a circle. The circumference of a circle is pi times its diameter. The diameter of the unit circle is 2. That's 2 pi times its radius. Its radius is 1. The entire circumference is 2 pi, which is about 6.28. Halfway around the unit circle is pi, 3.14 approximately. So we have to go a little further. How far are we going there? Maybe 4 is the distance. Somewhere in that ballpark would be the value of t. I don't know what it is exactly. To find the trigonometric functions, to do part B, we use the fact that cosine of t, I usually like writing parentheses around my input for the trig functions, though it's traditional not to typically bother. You could also write cosine of t like that, is the x-coordinate of the terminal point. That is -3/5, -0.6. Again, we don't know what t is. Could t be figured out? Yes, it could, but we're not quite there yet. What's the sine of t? Again, I like using parentheses, but you don't have to. That's the y-coordinate of this point. which is negative 4/5, negative 0.8. What's the tangent of t? Tangent can be thought of as sine divided by cosine, or if you prefer in this context, y divided by x. So that's going to be negative 4/5 divided by negative 3/5. If you prefer, you can write this as a product, negative 4/5 times the reciprocal of that thing, which would be negative 5/3. The negative signs will cancel, the 5s will cancel. You'll be left with positive 4/3, which as a decimal is 1.3 repeating. That's the tangent value. Cosine and sine are always between negative 1 and 1 because they correspond to x and y coordinates on the unit circle. But tangent and cotangent, we will see, can be bigger than 1. Cosecant and secant, in fact, are always either bigger than 1 or less than negative 1. Let's move on to those. Secant of t could be thought of as 1 divided by cosine of t. In terms of x and y, that's 1 over x. Take the reciprocal of this, it's going to be negative 5/3, negative 1.6 repeating as a decimal. Cosecant of t, by definition, is 1 over sine of t. It's funny, the s's and c's get swapped here in both of these formulas for the first letter. That's 1 over y. Take the reciprocal of this, that's going to be negative 5/4, negative 1.25. And finally, cotangent of t is 1 divided by tangent of t. It's the reciprocal of tangent of t. So take the reciprocal of y over x and get x over y. Negative 3/5 over negative 4/5. I also could just take the reciprocal of this thing. In the end, you're going to get 3/4 or 0.75 for the value of the cotangent function. These are true not by magic, but by definition. These are what these functions equal. For problem 2, our point P with rectangular coordinates x and y is on the unit circle in quadrant 2. I'll draw a picture to show you where that is. We're assuming the y coordinate of the point is 12/13. That, by the way, is going to be the sine of t. The y coordinate is the sine, where t is the arc length along the unit circle from the point 1, 0 to the point that we are at, the terminal point. We want to find various things. What is the x coordinate of the point, which is going to be the cosine of t? What is the sine of t, which is going to be y? That's going to be 12/13. Cosine of negative t, sine of negative t, tangent of t, tangent of pi minus t. This looks tricky here. And secant of pi plus t. Okay, let's make a drawing to get our bearings. That's almost always a good idea here. So I've got my xy plane again. I've got my unit circle centered at the origin. It's a circle centered at the origin with a radius of 1, looking about like this. You don't have to draw it perfectly. I certainly can't draw it perfectly. Right about like this. We are in the second quadrant. The upper right quadrant is called the first quadrant. The upper left, we go counterclockwise, is the second quadrant. The lower left is the third quadrant, and the lower right is the fourth quadrant. We're in the second quadrant. And the y coordinate of the terminal point is 12/13, which is close to 1. So we got to be just barely past that point there. That is the point P that we are at approximately, P of xy, where y is 12/13. T, the arc length of interest, starts at the point 1, 0 and goes along here to this terminal point. Yes, this is related to an angle, but we don't have to relate it to an angle. What angle is it related to? One angle it's related to is this particular angle. T is a length, though. That length along a unit circle does happen to match what's called the radian measure of the angle. But again, that's not our main focus at the moment. We're focused more on thinking about these trig functions in terms of t as a distance, as a real number along this unit circle. We're talking about the unit circle definitions of these trig functions. So that helps us get our bearings. As far as figuring out each part, let's start with part A to find x, which is, yes, also the cosine of t. It could have been said find cosine of t, and we'd be finding the same thing. What we need is we need the fact that we're on the unit circle here, so the equation of the unit circle, again, is x squared plus y squared equals 1. And if we know y as we do, we can solve for x. But you've got to be careful. You have to know what quadrant you're in. We're in the second quadrant where the x coordinate is negative. We're to the left of the y-axis where x is negative. So when I solve for x here for part A, I've got to take a negative square root, not a positive square root. If I solve this equation for x by subtracting y squared from both sides and then taking square roots, there's two possibilities. X is plus or minus square root of 1 minus y squared. But again, because I'm in the second quadrant, I need the minus square root like that, and that helps me solve this. So I take the minus square root of 1 minus 12/13 quantity squared. Doesn't look like it's going to be a nice number, but it actually is. We are talking about nice triangles here. Like in problem 1, it was a 3, 4, 5 triangle that what we did could be related to. Here we can relate this to a 5, 12, 13 triangle, right triangle in fact. So what do we get here? Do that squaring. We get 144 over 169. I got to get a common denominator there of 169. Ultimately, I get 169 minus 144 over 169. 169 minus 144 is 25, and there we have it. That fraction is a perfect square of 5/13. Just keep carrying the negative sign along. So there we have the answer to part A, the value of x, the x coordinate at that point. Also the value of cosine of t is negative 5/13. Part B, find the sine of t. That's easy. I told you the answer already. It's the y-coordinate of the terminal point, which is given to be 12/13. That's nice and easy. Part C, now we start getting a bit trickier. Cosine of negative t, the opposite of t. T is considered to be a positive number. What do you do when you've got a negative number here? How do you think about terminal points? With positive numbers, you go around the unit circle counterclockwise. With negative numbers, you start at this point and go clockwise. So negative t is a negative number, so it's not really an arc length, so to speak. You go a distance of the absolute value of negative t, which is the same as the absolute value of t, which if t is positive is t itself. To be at this point, the negative sign just means go clockwise. We're going to be at the opposite point across the x-axis here. In particular, notice that means the x-coordinates are going to be the same, and the y-coordinates are going to be opposites. Cosine of t, cosine of negative t, is the x-coordinate of this point right there. The x-coordinate is the same. This is going to be the same as cosine of t itself, which we already found to be negative 5/13. And again, you can see it in the picture. The first coordinate of this point, the x-coordinate, has to be negative. So we got to get the same answer as before. What about sine of negative t? Let's do that one together here. Sine of negative t. We're at this point again. The sine is the y-coordinate of that point. That's the opposite of the y-coordinate of this point by the symmetry. That's going to be the opposite of sine of t. Sine of t is positive 12/13, therefore this is negative 12/13. Yes, this point, its two x and y coordinates are both negative. We got to get negative answers here. This equality here actually ends up being true no matter what t is, as well as this equality. This ends up meaning that if you think of these things as functions, cosine is an even function and sine is an odd function. We'll talk more about what that means graphically in a little bit. Part E, what's tangent of t? Tangent of t can be defined as sine of t divided by cosine of t. In other words, y divided by x. And we found these things already. Again, y is given to be 12/13. That's the sine of t, and we figure out x to be negative 5/13. Here the 13s cancel. The negative sign does not cancel. We're left with negative 12/5. As a decimal, that would be negative 2.4 is the tangent of this value of t here, of that real number t. Part F gets a bit trickier. What's the tangent of pi minus t? Okay, again, here the picture can help. T is this distance here, which, by the way, it's a little bit bigger than pi over 2, a little bit bigger than 1.57. You might imagine it to be 1.6 or 1.7 or something. Pi minus that would be about 3.14 minus 1.6 or so. It's going to be a positive number. In fact, it's going to be this distance right there, but you want to imagine starting again from the point 1, 0, so we have to go that same distance up here, and by symmetry you're going to be at a point that is the reflection of this point across the y-axis. This distance right there is pi minus t, bringing you to this terminal point, again symmetric with respect to the y-axis. The same y-coordinate and opposite x-coordinates as our original point. Once again, we do y over x, but now for that new point, its y-coordinate is the same as the original point, still 12/13, but its x-coordinate is the opposite of the original x-coordinate. It is positive 5/13, not negative 5/13. This simplifies to positive 12/5, positive 2.4. And finally, part G, what is the secant of pi plus t? Pi plus t. Think about the picture. Pi, a distance of pi, is halfway around the unit circle. Go another t, brings you to right around there. It's going to be, by symmetry, the reflection of this point across the x-axis. This distance around here is going to be pi plus t. But anyway, relating it to our last one, the x-coordinate is the same as this one, and the y-coordinate is the opposite. Secant is 1 over cosine, so that'll be 1 over the x-coordinate of, not the original point, but this point. The x-coordinate of that point is 5/13, so we have 1 over 5/13 is going to be 13/5, or 2.6 is going to be the value of the secant of that number. For problem 3, we're focusing on the most fundamental graphs that we want to know about. Graph the functions cosine of t, sine of t, and tangent of t in the same set of axes. What are their periods? They are periodic functions, we will see. You still want to focus on the unit circle to help you think this through. So once again, I will draw the unit circle. You want to imagine starting at the point 1, 0 and going around counterclockwise as t increases through positive values, and imagine how the x and y coordinates are changing. The x-coordinate, for example, starts out at 1, decreases to 0 right there, then to -1, then to 0, then to +1 before it repeats. How often does it repeat? Well, the circumference of the unit circle, again, is 2 pi units, so it repeats every 2 pi. Its period, in fact, is 2 pi. The y-coordinate, the sine of t, starts out at 0, goes up to 1 before going back down to 0, before going down to -1, before coming back up to 0, and then it repeats. Tangent is y over x. We'll think about that last. Focus first on the x-coordinate. That's the cosine. X equals cosine of t. For positive values of t here, we start out again at 1. The value of the cosine function at t equals 0 is 1. This axis is a t-axis here. As t increases, so that we go up here to t equals pi over 2, about 1.57, the x-coordinate has gone down to 0. Pi over 2 is labeled. So it looks about like this. The scales, by the way, on these axes are not the same. Pi over 2, again, is about 1.57. If I were to make the scales the same, I'd have to probably put it out around here somewhere. Okay, so this graph, just realize that the scales are not the same. As t continues to increase up toward pi, about 3.14, the x-coordinate is going down to -1, so we got to be at this point right about here. Try to connect these dots with a smooth curve. Try to make it as smooth looking as you can. I can plot more points. For example, you might want to plot what happens when t is pi over 4, for example. It turns out to be about 0.7 or so, square root of 2 over 2. I'm not going to take the time to do that. As t continues to increase to 3 pi over 2, 1.5 times pi, it brings me right there. The x-coordinate is back to 0, and then it gets up to 1 by the time I get to 2 pi. So about like this, and over here about like this. And then it repeats. The cycle repeats. This is a periodic function. Period is 2 pi. it looks about like this. Okay, I'm not going to focus on trying to get this as good as I can. That's approximately right. What happens when t is negative? The cycle repeats in the negative direction. You're traveling clockwise instead of counterclockwise. As t decreases through negative values, x still decreases to 0, then to -1, then back up to 0, then back up to +1 in a nice continuous way. I could plot some points here quickly as I can. Try to connect these with smooth curve. What I'm graphing here is the graph of cosine of t, periodic with period 2 pi, and yeah, looking about like this. And it continues forever, okay? And yeah, this is not a great graph, but reasonable within the amount of time that I have. That is cosine of t. What about y equals sine of t? It's the second coordinate, starting at 0 when t is 0. Starts right there. As t increases, we travel counterclockwise. The y coordinate increases to 1 by the time we get to pi over 2. And then goes back, the y coordinate goes back down to 0 by the time we get to pi. And then to -1 by the time we get to 3 pi over 2. Then back up to 0 for the y coordinate of the terminal point once we get to t equals 2 pi. You can see it's going to be a similar kind of behavior. In fact, the red graph is a horizontal translation of the green graph to the right by pi over 2 units. That is a fundamental property to know. This is also periodic with period 2 pi. It is the sine function, and it continues over here. Okay, so something about like this. Not a perfect graph. Trying to do a decent job in the amount of time that I have. About like this. Okay, and yes, it is true, like I just said, this is the same as the cosine graph shifted to the right by pi over 2 units. So it equals cosine of t minus pi over 2. You also could say that the cosine graph is the sine graph shifted to the left by pi over 2 units. You could also say the cosine of t is the sine graph shifted to the left by pi over 2 units. So replace t with positive t plus pi over 2. All right, what about the tangent function? Tangent is not x or y itself, it's y over x. It's sine of t divided by cosine of t. Effectively, it's the red graph divided by the green graph. So we got to imagine dividing graphs, meaning dividing their outputs, their second coordinates. How should I label a vertical axis here? Probably no label, or maybe some other letter like z. It represents different quantities depending on which graph that I'm looking at. So the red graph divided by the green graph. Start at t equals 0. Red divided by green is 0 divided by 1 is 0. The tangent function goes through the origin as well. As t increases, take the red divided by the green. I get a bigger number divided by a smaller number, but still positive fraction. It turns out that since this doesn't change, the green graph doesn't change very much when t is slightly positive, effectively it's like I'm dividing the red graph by something close to 1, so the purple graph that I'm making here is close to the red graph at first. But as I continue increasing, I take the red divided by green. It's right when we're at pi over 4, in fact, where the red and graph cross, and therefore red divided by green has got to be 1. And then as t continues to increase toward pi over 2, red divided by green is a number close to 1 divided by a number close to 0. And in fact, at pi over 2, I'm dividing by 0, which you can't do. So what that ends up meaning, it turns out, is you've got a vertical asymptote for the tangent function at pi over 2. This green arrow is now unfortunately focused on that point that I drew there. It is the green graph that I should focus on there with the green arrow. This is part of the graph of tangent. And if you take red divided by green over here, you have a negative number divided by a positive number, which is negative. When t is just barely negative, you're dividing by a number close to 1. So the purple graph continues to be close to the red graph. And you end up having a vertical asymptote at negative pi over 2 as well, right about here, like that. There is one part of the tangent function. It turns out, you can think about continuing to divide red by green, that the graph is periodic with period pi, not 2 pi. And this graph continues itself with this kind of pattern to the right and also to the left. It is a little trickier, for example, over here. You have to think about red divided by green again, opposite signs in here, and they both negative signs over here, so the negative divided by negative is positive. That's why the graph is positive over here. It's going to be undefined. You're going to have vertical asymptotes wherever the green graph, which is the cosine graph, is 0, because you'd be dividing by the cosine graph. This is a basic picture of what it looks like. It continues over here, again, period pi. Keep going, keep going, keep going. These graphs, again, go on forever and ever to the right and to the left. The periodicity of these graphs can be written symbolically as well. The fact that cosine and sine are periodic with period 2 pi means, for example, I can write cosine of t plus or minus 2 pi. I will, in fact, write a plus or minus in here, is the same as cosine of t. You can also replace that with a plus or minus 4 pi or 6 pi or 8 pi or 10 pi or any even multiple of pi. Same kind of thing holds with the sine function. Sine of t plus or minus 2 pi is the same as sine of t. Tangent has period pi. I can write tangent of t plus or minus pi equals tangent of t, and I cannot replace these 2 pi's for cosine and sine with pi's, but I can for tangent. I can also replace this plus or minus pi with a plus or minus 2 pi, plus or minus 3 pi, plus or minus 4 pi, plus or minus 5 pi, etc. Any integer multiple of pi works. As a final comment, I'll also say that really where the tangent graph is most useful is considering the graph of its so-called inverse function, inverse tangent, or arctangent. The purple graph, and none of these graphs is 1-to-1, but the purple graph, if you restrict the domain to being negative pi over 2 to positive pi over 2, and just take this piece and reflect it across the line y equals x, or in this case y equals t, you'll get a graph that's the inverse tangent or arctangent function. That is a pretty interesting graph that has some more important properties for applications. Number 4 is kind of a strange problem. Use a fundamental trigonometric identity to write the expression tangent squared t times secant of t in terms of just cosine of t. What a strange problem. What are we supposed to do here? Well, first of all, one set of trigonometric identities, you could say, is the very definitions of these functions. Tangent of t is sine of t divided by cosine of t, and secant of t is 1 divided by cosine of t. By the way, notationally here, we've got a tangent squared. That really means tangent of t quantity squared. It's really important to know that. That means you take the tangent of t first before you square. Now go ahead and replace tangent with sine of t divided by cosine of t, and I'm squaring that whole fraction. Replace secant of t with 1 divided by cosine of t. By rules of algebra, when you square a fraction, you square the numerator and you square the denominator, which I'll use this kind of notation for again. But again, when I write sine squared t, it really means sine of t quantity squared. When I write cos squared t, it really means cosine of t quantity squared. And then I also have to multiply the fractions. So I get sine squared t divided by cos cubed t. Am I done? It says in terms of cosine of t, not cosine and sine. What other trigonometric identity might be useful here? The fundamental one, called the Pythagorean identity, cos squared t plus sine squared t equals 1. I haven't mentioned that. It's based on the unit circle and the fact that cosine is x and the sine is y. There's the equation of the unit circle. This equation is true. It's an identity. It's true for all t. It doesn't matter what t is. It's not an equation to solve. It's an identity. It's true for all t. If you graph cos squared t plus sine squared t with your calculator, you'll get a horizontal line with output 1. It's amazing. That's what we want to use here. That's the fundamental trigonometric identity that they are really most referring to here. And I can use it here by replacing the sine squared t with, well, solve this equation for sine squared t. 1 minus cos squared t. I don't have to take a square root, so I don't have to worry about a plus or minus sign or something like that. There is one way to write the answer for this expression in terms of cosine of t. Is there another way that also still involves cosine? Yeah, I mean, you could split it up into two fractions as 1 over cos cubed t minus cos squared t over cos cubed t, which is 1 over cos t. You don't have to do that. This is probably a better answer. But this answer does emphasize something else that's kind of interesting. 1 over cos cubed t would be the same as secant cubed t, and 1 over cos t would be the same as secant t. So, kind of amazingly, it might seem, tangent squared t times secant of t ultimately can be written in terms of just secant as well. Secant cubed t minus secant of t in kind of an unexpected way. Kind of interesting. But that's not the point of this problem. The point is to write it in terms of cosine, and so that's probably the best answer right there. As a final note, I should also say that these functions are undefined at certain values of t, for example, like pi over 2. So that's where this tangent and secant would be undefined. So these equations are only true for all values of t where these functions are defined. Number 5 looks somewhat similar to number 4. Express just plain tangent of t in terms of evidently just sine of t, but not for all values of t where tangent is defined, but evidently just for t in quadrant 2. Tangent of t, by definition, is sine of t divided by cosine of t. But that's not quite done because we have a cosine of t. I'd like to replace that cosine of t with something involving sine. I do know from that Pythagorean identity that cos squared t does equal 1 minus sine squared t. But I need to replace cos t, not cos squared t, so I need to take a square root. But if we're in quadrant 2, be careful. Quadrant 2 is not the upper right, it's the next one over, the upper left, where cosine, the x-coordinate, is negative, so I need to take the negative square root. That's the trickiest part about this problem. That does mean we're pretty quick to the final answer. Tangent of t is sine of t divided by negative square root of 1 minus sine squared t, which you can bring the negative sign out in front as negative sine of t divided by square root of 1 minus sine squared t. These two things are equal to each other for all values of t in quadrant 2. That is an identity in just quadrant 2. If I wanted an identity, for example, in just quadrant 1, I'd take the positive square root. I would not have a negative sign there. Number 6 says to find the amplitude, period, and phase shift of this function. Y equals f of x equals 3 times sine of x over 2 minus pi over 6, and then sketch the graph of f. We're going to have to use our knowledge of transformations to help us do this problem. First, let's think about how do we get this function in terms of transformations. We start with the parent function, y equals sine of x. And for example, we can multiply it by 3. That is going to correspond to a vertical stretch by a factor of 3. It's going to take the original graph of the sine function and stretch it vertically by a factor of 3. All the y coordinates get multiplied by 3. So in a sense, they go 3 times as far away from the horizontal x-axis. That is a vertical stretch. Vertical stretch. It's probably useful here for us to factor out a 1/2 out of this so that we don't have an x over 2 here. If we factor out of 1/2 out of what's inside the parentheses here, we'll get a 1/2 times x minus not pi over 6, but whatever I have to multiply 1/2 by to get pi over 6, that'll be pi over 3. So if I replace, do 2 more steps here. If I replace x with 1/2 x, first of all, that corresponds to a horizontal stretch, really. When you multiply x by a factor that's between 0 and 1, that corresponds to a horizontal stretch. All the x coordinates get twice as far away. If it was a 2x, it would be a horizontal compression. And then finally replace x with x minus pi over 3. That corresponds to a horizontal translation by pi over 3 units. Okay? So think about doing all this. Maybe you want to make each step lightly or something on your paper. I'm going to try to jump to the final step right away, the final graph. So I have my sine function that's going to, for example, start at 0, 0 and go up to a value of 3 once I get to pi over 2, or a value of 1 once I get to pi over 2 before going back down to pi, etc., having a period of 2 pi. If I multiply by 3, it does go up to 3 once I get to pi over 2 before going down to 0, something like this. But then I am doing a horizontal stretch by a factor of 2 because I have the coefficient of 1/2 there. It's going to get elongated in the horizontal direction. The period's going to get bigger. The period's no longer going to be 2 pi, it's going to be 4 pi. So I have to reach my maximum of 3 once I get to pi instead of pi over 2, going back down to 0 once I get to 2 pi, etc. The period is going to be 4 pi instead of 2 pi. We can confirm that symbolically here in a minute. Then I want a horizontal translation to the right by pi over 3 units. Pi over 3 units is a little bit smaller than pi over 2 units. You know, pi over 2 is about 1.57. Pi over 3 would be about, I believe, 1.04, 1.05 in that ballpark. That's pi over 3. Translate the graph to the right by that many units. So it's going to have a horizontal intercept there. Period of, again, 4 pi instead of 2 pi, whereas the original untranslated graph goes to its peak once we reach pi. We have to continue translating it to the right by pi over 3. Pi over 3 units to the right of that is going to bring you right about there. That's where it's going to have its maximum. And then it's going to come back down to the horizontal axis, pi over 3 units to the right of 2 pi. Something about like that. Try to make it as smooth as you can. Continuing, we're going to get back down to negative 1 once we get to 3 pi translated to the right by pi over 3 units is where we're down to negative 3, in fact, because the amplitude is 3, it turns out. I'll talk more about that in a minute here. And then pi over 3 units to the right of 4 pi. It's going to bring us over here before we cross the x-axis again. All right, continue the graph. You might want to use a calculator to help you draw this more accurately. I'm not sure exactly where it's going to cross the vertical axis here, but it's going to have its low point, pi over 3 units to the right of negative pi, right around here or so. And continue. Something about like this is what the graph is going to look like over here. Okay. Let's confirm this with technology. Go to my y equals screen, plug in this function, the original function here, 3 times sine of x over 2 minus pi over 6. Pick a window that's the same as what I got on the paper here. I'm going to go from negative 4 pi to positive 4 pi. Let y go from negative 3 to 3. Let's see if we did a decent job here. Compare these two graphs. The scales are different, obviously. Yeah, it looks like we didn't do too bad of a job. That looks like a pretty good graph by hand in that amount of time. What about these quantities? The amplitude, the period, the phase shift. The period we've already talked about. The period is 4 pi. That can always be thought of as 2 pi divided by whatever the coefficient of the x is. This can be thought of as 2 pi divided by 1/2. Whatever the coefficient of x is, put it down there. 2 pi divided by that will end up being the period. Yes, if you simplify this, 2 pi divided by 1/2 is the same as 2 pi times 2, which is 4 pi. The period is 4 pi. That's how long it takes horizontally to go through one complete cycle. What's the amplitude? In this kind of setting, the amplitude is always the absolute value of whatever the coefficient there is. In this case, the absolute value of 3, which is 3. If that were a negative 3, it would still be an amplitude of 3 because the absolute value of negative 3 is 3. What does that represent geometrically? It represents the vertical distance between what you might call the average value of the function, the midline going through the middle of the graph, and the peak, the high point, or the valley, the low point. The second coordinates of this point and this point are plus 3 and minus 3. That vertical distance there is also a 3. That's called the amplitude of this function. And the phase shift is just another name for the horizontal translation. It's not to the right by pi over 6 units, it's to the right by pi over 3 units. It's pi over 3 to the right. If this had been a plus pi over 6 in here, the phase shift would have been negative pi over 3. The fact that it's negative means it would be a shift to the left. And we sketch the graph. I will tell you also that sometimes this minus pi over 6 is called the phase angle. That's another name that people bring into this sometimes, but it doesn't have to be thought of as an angle. Number 7 is a transformation of the tangent function. Find the period and sketch the graph of this function y equals tangent of 2x minus pi over 2. Do something similar to number 6 inside here. Instead of factoring out 1/2 though, let's factor out 2. What do I have to multiply 2 by to get pi over 2? I got to multiply it by pi over 4. Double check that by distributing that through. I'd get 2x minus 2 times pi over 4 would be pi over 2, like you see. So the transformations involved here do not involve any vertical stretches, but they do involve horizontal translation to the right by pi over 4 units. And also, because of the 2 there, because that's bigger than 1, a compression toward the horizontal axis. The period, instead of being pi, will be smaller. It'll be pi over 2. The period of this particular function will be pi over 2 because of the horizontal compression toward the vertical axis, making the oscillations happen faster. But again, we have the rightward translation to pi over 4 to the right. Pi over 4 is half of pi over 2. So there's pi over 4. Period is pi over 2. Half a period then would be pi over 4, which would mean there's a vertical asymptote here at pi over 2. And a vertical asymptote at 0 as well. One period is going to look about like this. You can double check this. For example, can you imagine plugging in 0 here for x? You'd have 2 times 0 is 0, minus pi over 2 is negative pi over 2, but tangent of negative pi over 2 is undefined because cosine of negative pi over 2 is 0. On the unit circle, negative pi over 2 brings you to the low point where the cosine is 0. Yeah, this is going to repeat, and the period is going to be pi over 2. Every pi over 2 units, which means the oscillations are going to happen very rapidly here. In this window here, we're going to get another period. I'm not going to draw this perfectly. In this one here, we'll get another one. Like that, etc. It continues forever and ever to the right and to the left as well, with a period of pi over 2. I will not continue drawing it past this point. Continue it to the right and to the left forever and ever. Number 8 is the reverse kind of problem. We're given a graph that you see here. It's a part of the graph of a function of the form y equals f of x equals a cosine of bx plus c plus d. Determine the function, and also write this function using the sine instead of the cosine. So again, think in terms of transformations here. It's probably best to think about what d is first. That corresponds to a vertical translation of the cosine function. Where is the midline, so to speak? It would be halfway between the extremes. The extremes, the high value is 9, the low value is 1. That's called a maximum and a minimum. Halfway between those two numbers is their average, which is 5. So at 5, that's the midline of the graph. That's going to be the value of d, in fact, corresponding to a vertical translation by that much. If the period is, like I said in the last couple problems, 2 pi over whatever the coefficient of x is, 2 pi over b in this context, that's equivalent to saying b itself is 2 pi divided by the period. So if I know the period, I can figure out b. What is the period? It goes through one complete cycle here, from high to low back to high again as x increases from 3 to 11. The period is 8. 11 minus 3 is 8. I'll go ahead and write 11 minus 3. 2 pi divided by 8, which simplifies to pi over 4. That's the value of b. A is the amplitude. That's this vertical distance between the midline and the high point or the low point. 9 minus 5 is 4, just like 5 minus 1 is 4. The amplitude is 4. Amplitude is 4. Does that mean A is 4? It does mean we can use A equal to 4, but we also could use A equal to negative 4. So which should we use? It's simpler to use positive 4 here, especially because this first high point could be thought of as a simple rightward translation of the cosine graph, which has a high point at x equals 0 by 3 units there. That's a distance of 3. And if I start with the high point when x is 0, or in this case when x is 3, I better use A equal to positive 4. How would A equal to negative 4 possibly work? I could imagine taking the cosine graph and flipping it across the horizontal axis first before I translate upward, and then the rightward shift would correspond to the first coordinate at this point of 7. So if I did a rightward shift of 7, I'd want to use an A equal to negative 4. But again, it's simpler to use positive 4. That's going to be my value of A. The hardest part is the C. What should C be? Let's go ahead and start just plugging in these numbers. So my function looks like 4 cosine of pi over 4x plus c plus 5, and I got to figure out what c is. C does correspond to a horizontal translation. If I factor out a pi over 4, I can write what's left here as plus 4c over pi. Oh, this seems tricky. It might be better to write it in this form first before writing it in that form, but I did it this way. I want that number, 4c over pi, to equal something that will correspond to a rightward translation by 3 units, negative 3. Solve that for c. C will then be negative 3 times pi over 4. Negative 3 pi over 4 looks to be what we need. So it looks like one answer here involving the cosine function is 4 cosine of pi over 4x plus c means minus 3 pi over 4 plus 5. If you want to double check, did we get that horizontal translation to the right by 3 units correct? I'd want to factor out a pi over 4. And what do I have to multiply pi over 4 by to get negative 3 pi over 4? I have to multiply it by negative 3. So yeah, that does correspond to a rightward translation by 3 units. So this is the answer, or one answer. There are actually infinitely many answers. I could also imagine translating to the right by 11, for example. How about using the sine function? We'd want to figure out what the coordinates of this point are. To help us figure that out, then the rightward translation of the sine function would be this amount right there. What is the coordinates of that point? Well, its second coordinate is certainly 5. What's its first coordinate? The period is again 11. Half a period is, 11 minus 3 is 8. The half a period would be 4, 7 minus 3. This corresponds to a quarter period here. That's going to be 2. The first coordinate's got to be 3 minus 2 is 1. 1, 5 has to be the coordinates of that point. So it turns out in terms of sine, this can be written as 4 sine of pi over 4 times, I'm writing it in factored form initially here, x minus 1, rightward translation by 1 unit. And then if I want to write it in a more standard form, multiply the pi over 4 through and get this. These two functions, if I did not make any mistakes, are the same function. That's writing in terms of cosine. This is in terms of sine. They both have this exact same graph. Our last problem is a little strange. Let f of x be this strange looking function here, sine squared x over x. We're going to use technology in this problem. First thing, is f an even function, an odd function, or neither? Let's address these one at a time. How do you decide? You think about replacing x with negative x, effectively a horizontal flip across the vertical axis. What happens when you do that? Do you get the original function f of x back, or do you get its opposite, or neither? Well, let's see. We got to replace x with negative x in both spots. Sine of negative x, since the sine is an odd function, is negative sine of x. But I am squaring that, so the negative sign is going to go away, giving me sine squared x divided by negative x. In other words, negative sine squared x divided by x, the opposite of our original function. That's enough to say, therefore, f is odd, and its graph is going to have what's called origin symmetry. If I graph the part to the right of x of the y-axis where x is positive, I can get the part to the left of the y-axis where x is negative by reflecting each point through the origin. It's a little tricky, but we'll see it in the graph. Part B, find the x-intercepts of the graph of f. The x-intercepts are going to be where this function equals 0. The only way this function can be 0 is if its numerator is 0. And the only way a square can be 0 is if the thing itself is 0. So it looks like the zeros are the same spots where sine is 0. But is that really true? Sine of 0 is 0, but wait a minute. This function's undefined at x equals 0 because I would be dividing by 0. So while sine of x equals 0, and I'll go ahead and write that in there. Here are the zeros of sine. There are infinitely many of them. 0 has to be crossed out. It's not a root. It's not a 0. It's not an x-intercept of this function because this function's undefined at 0. Weird, but true. Part C, graph f in an appropriate viewing rectangle. And we're going to see something that'll be a little confusing when we do. Let's see what happens. So if I type this into my calculator, sine squared x should be typed in as sine of x, quantity squared. Divide all that by x. Let's see what we see. I'm going to choose a y range that's smaller here. Some oscillations in kind of interesting graph. I do see zeros, for example. That is pi there. That's 2 pi. There's 3 pi, 4 pi, etc. Negative pi, negative 2 pi, negative 3 pi, negative 4 pi, etc. But it looks like there's a 0 at 0, a root, an x-intercept. Guess what? Even though it looks like there's an x-intercept there, there's not. There's a hole in the graph because the function's undefined there. There'd have to be a missing point. Wow, that's weird. This would be not continuous at x equals 0. It's called a removable discontinuity, though, because I can fill in the hole if I wanted to, but technically I can't unless I define a new function that's a piecewise function. We'll come back to that. Part D, describe the behavior of this function as x goes to plus or minus infinity. We saw the graph look like that. What happens to this graph as x keeps going to the right forever and ever or to the left forever and ever? These oscillations seem to be getting smaller and smaller. In fact, if you think about it, sine of x is always between -1 and 1, and so sine squared is always between -1, in fact, 1. In fact, it's always between 0 and 1. This thing over x has always got to be between, I guess, plus or minus 1 over x. Let's graph 1 over x and -1 over x as well and see what we see here. Oh, wow, isn't that cool? Okay, ignore those other two pieces. This piece and this piece, the graph just touches. I guess you can say no matter what x is, this function, this oscillating function, is always between these graphs. And these graphs, 1 over x and negative 1 over x, do get squeezed down towards 0 as x goes to plus or minus infinity. Yes, these oscillations have to keep getting smaller and smaller. The function does approach 0 in value as x goes to plus or minus infinity. It does equal 0 at integer multiples of pi and gets arbitrarily close to 0 at other values of x as x continues getting bigger and bigger. In calculus notation, we would write the limit as x goes to plus or minus infinity of sine squared x over x equals 0. The y coordinates can be made as close as we like to 0 for all x sufficiently large to the right or to the left. Does that mean the x-axis where y is 0 is a horizontal asymptote? Yes, it actually does, though not in the usual kind of way. It does mean it's an asymptote, but just not in the usual way that we're used to. Part E, notice f of x is undefined when x is 0. I already mentioned that. What happens as x goes to 0? Well, wouldn't you just say it's undefined? What does this mean? Arrow 0, goes to 0 is what I said. That means x is approaching 0 without actually equaling 0. Huh? Kind of a weird thing to say. I'm imagining letting x get arbitrarily close to 0 without actually equaling 0. This is limit notation as well. Even though f of 0 is undefined, the limit as x approaches 0 but does not equal 0 of this function does exist and is 0. Just like the calculator, you might say, was deceived into thinking the point 0, 0 is on the graph. It's not. There's a point missing. There's a hole in the graph. I can fill in the hole by redefining the function there in a piecewise way to be this thing when x is not 0 and 0 when x does equal 0, but that is technically a different function. So even though there's a hole in the graph, the function does approach 0 in value without actually equaling 0 as x approaches 0 without actually equaling 0. Now that sounds like a big mouthful, like who would care about such a thing? Who cares about these removable discontinuities, these graphs with holes in them? They're actually super duper important in calculus. This limit concept in calculus and derivatives that come from them, holes in graphs, graphs with holes in them, come up all the time. They're important. So you want to realize what's going on here. That'll help you in calculus. Thanks for watching.